Hello, my name is Alex. Beatrice and I will be talking about our project on segmenting brain tumors with neural networks. Our task is to take a series of magnetic resonant images, or MRIs, and identify and classify any brain tumors. Specifically, we are classifying gliomas, the most common form of a brain tumor in adult patients. Gliomas come in a high and low-grade form, with a life expectancy ranging from 2 to several years. Understandably, this could dramatically influence patient treatment if we could produce fast and accurate labelings of tumors in an automated fashion. In 2012, the Multimodal Brain Tumor Image Segmentation, or BRATS challenge, was created to apply machine and deep learning techniques to this area. This remains an active annual competition, as tumor segmentation is a challenging problem. Even among experts, DICE scores, a measure of segmentation accuracy, can range from 74 to 85%. This is mainly due to the variability of tumors. They don't have consistent shapes or locations, and they are defined relative to the characteristics of local brain tissue. For this project, we've re-implemented two existing networks from the literature. To take it a step further, we then made improvements to one of the models.
We used a dataset from Brett's 2017 competition, which consisted of MRI scans from 285 patients. Each patient had 4 scans, and the scans were labeled by the experts with 3 different types of tumor. Since we could not get access to the label and validation and testing set, we splitted the training data to create our own. We made sure that different set was assigned with different patients. Our first model implementation was cascaded CNN. We subsampled patients and handled the imbalance in data by downsampling. The Wang model used 3 different networks to sequentially identify 3 types of tumors. First segmenting the whole tumor, followed by the tumor core, lastly the enhanced core. During training and validation time, different masks were used to generate the input sequentially. During training, we used the ground truth. First network will not have any mask on the input, but for the second network, we masked the input with the bounding backs of the whole tumor from the ground truth and fed it to the next model. Same thing happened for the third model. During evaluation or testing phase, we did not use the ground truth, but used the predicted output from the previous model. The original paper used an isotropic network to balance the trade-off between receptive field size and memory consumption. Using large receptive field on 3D images would consume a lot of memory. Therefore, Wang proposed to use large 2D receptive field, but with smaller depth. This is implemented by the decomposition of 3D kernel to 2 kernels, one with 2D and one with depth. The diagram on the left has the detailed architecture of the network. This is our final results of our cascaded CNN training. We were able to get similar performances compared to the Wang model, but we could not get the same level of scores, possibly because we only used 10% of the training data. Notice the training and validation scores, their gap gets larger in the later models because they depend on the previous model's performances.
For our next model, we implemented the generative adversarial network proposed by Li et al. As with the CNN model, we trained using scans from only 40 patients due to memory restrictions. Further, because of our much smaller patch size, some patches are entirely outside of the skull. We rebalanced our dataset to have a 60-40 split between healthy and tumor patches, with a 1% chance of sampling a patch outside of the brain. The Li model consists of 8 convolutional blocks feeding into an MLP to compute a pixel-level segmentation over the entire patch. This 15 by 15 segmentation is then given to an adversarial network to predict a higher order loss function. Ultimately, we use a combination of the adversarial loss and a cross-entropy loss as our overall loss metric for this model. As a refinement to the Li model, we replaced the 8 convolutional blocks with a compression layer followed by 2 ResNet-inspired blocks. Each res block consists of 2 convolutional blocks and a skip connection lacking a nonlinear activation. We made this change as deep neural networks can be challenging to train. With 19 layers between the input and adversarial prediction, we felt that skip connections could improve model performance. On the left are some example validation results from the Li model and our model. It's important to note that the ground truth images are 31 by 31 pixels, while the segmentation labels are 15 by 15. Our model showed a 5% improvement over the Li model in its validation multi-class DICE score.
To sum up our project, we have successfully implemented both GAN and cascaded CNN to show matching performances to human expert labeling. We also noticed that, in comparison to one-shot models, the cascaded CNN architecture may have a risk of amplifying the error in later networks and would require much higher performances on previous networks to show promising results all the way through. In GAN also, adding skip connection got better performances than the baseline Li model. This is the end of our presentation, and thank you so much for taking your time listening, and hope you all have a wonderful summer.